We're going to find all the relative extrema and use the second derivative test if it applies. And so the first thing I'm going to do is rewrite my original function so it has a fraction exponent instead of a radical. Then when I derive, I'll use the chain rule. So the 1/2 drops, leave the inside alone, subtract 1 from the exponent, multiply by the derivative of the inside. Now, that's technically 2x over 2, so those 2's cancel. And as a fraction, the x is in the numerator. That x squared plus 1 to the negative 1/2 is unhappy in the numerator, so when it comes down in the denominator, its negative feelings go away. It's happy. And so now I want to find my critical numbers by setting it equal to 0. And the critical numbers come from zeros in a fraction. That's when the numerator equals 0. So my numerator, real simple, see, no solving to do in this case. And then they also come from places where it's undefined. And so that's when my denominator equals 0. So we just need to make sure to be careful so that we check both. And so we're going to look at this x squared plus 1 to the 1/2 logically, because if I take any negative number and I plug it into that x squared, it's going to turn positive when I square it. And then when I add 1, it just gets bigger, but never 0. If I choose 0 as my x, 0 squared is 0, but then you add 1 and it's 1, not 0. And then a positive number stays positive, it's just bigger when you square it. And then when you add 1, it just gets even bigger. And so again, not 0. So it's never going to equal 0. So then in order to do my intervals, I need to know my domain. So let's look back up at the top at f of x. My domain of my function, remember radicals and fractions are the trouble kids in algebra. They're the ones that have issues with their domain. However, this x squared plus 1, we already proved that it's always positive because the negatives turn positive and get bigger. And so it's always positive. It doesn't have any places where it goes undefined. And so that means my domain is all real numbers, negative infinity to infinity. So now I know how to set up my intervals. Starts at negative infinity, has something happening at 0, picks back up at 0, and then goes to positive infinity. Now, again, let's test this logically. So we already know the denominator is always positive. So denominator, always positive. And if I plug in a negative number, the numerator is the one that changes. So a negative number is going to make that numerator negative. So a negative divided by a positive, that's going to be a negative interval. But when I move over to 0 to infinity, my numerator is positive. We already know the denominator is always positive, therefore positive interval. So f of x is decreasing and then increasing, because this is what my slope tells me. My first derivative is my slope. That means if it decreases and it increases, that's the shape of my graph, roughly. And there's a relative min at 0. Now, I want to prove it with my second derivative. So I have f prime that I'm going to derive. I'm going to rewrite it so that it's a product. It's your choice either to do the quotient rule or a product rule. I choose a product. And so deriving using the product rule, the derivative of x is just 1. The x squared plus 1 to the negative 1/2 stays. Then we're adding, the x stays. Notice how I'm giving myself a little bit of room because I know that exponent is about to drop. So that puts that as a negative 1 over 2, so negative 1/2 x. and then the x squared plus 1 stays, and then negative 1/2 plus negative 2 over 2 is negative 3/2, and then multiply by the derivative of the inside. Now, just like in the first derivative, these 2's are going to cancel. I have to rewrite it because I've got to look at these as fractions. And so I have 1 over x squared plus 1 to the 1/2. And then here, remember that was a minus sign, so that changed that from adding to subtracting. I have an x times an x, so x squared in the top, and then the x squared plus 1 to the 3/2 in the bottom. I want to make a common denominator, so I know I need to multiply the left fraction by x squared plus 1 over x squared plus 1, both to the first power. So x squared plus 1 to the numerator, x squared plus 1 to the denominator, and so on the top of the left term, I have x squared plus 1, and then I'm going to have a common denominator, so I can go ahead and say minus x squared, and then it's x squared plus 1 to the 3/2. So the x squareds cancel. Isn't that nice? And I have a 1 over x squared plus 1 to the 3/2. So setting that equal to 0, I know my domain is negative infinity to infinity. The numerator doesn't have any x's now, and so that tells me that the numerator is always positive and the denominator is always positive. So I don't have any critical numbers because 1 doesn't equal 0. And it is concave up everywhere. So that verifies that I have a relative minimum at x equals 0. And that's all we do.